Have you ever wondered what the world is really made of? Imagine zooming in about 100 billion times, yeah, that's 11 zeros, on the skin of your fingertip. What do you think you'd see? It wasn't until a few hundred years ago that scientists like John Dalton started to crack the code. Dalton introduced the idea that everything around us is made up of tiny particles called atoms. Even though we can't see atoms with the naked eye, they're responsible for the properties of matter we experience every day, like color, phase, whether something is solid, liquid, or gas, and even smell. So, what exactly is Dalton's atomic theory? Dalton based his theory on two fundamental laws, the law of conservation of mass and the law of constant composition. The law of conservation of mass states that matter is neither created nor destroyed in a closed system. This means that during any chemical reaction, the total mass of the reactants equals the total mass of the products. It's a principle we apply every time we balance chemical equations. For example, a scientist takes 10-gram sample of ethanol and burns it in the presence of oxygen in an open beaker. After the reaction, the beaker is empty. Does this violate the law of conservation of mass? The answer is no. Even though the beaker appears empty, the ethanol has reacted with oxygen to form carbon dioxide and water vapor, which have escaped into the air. The mass of the reactants and the products remains the same. It's just that the products are now in a different form and location. But what exactly did he envision when he spoke of atoms? He proposed that all matter is composed of tiny, indivisible particles called atoms, which he imagined as solid, massy, hard, impenetrable, movable particles. However, it's important to note that Dalton didn't have the advanced instruments we possess today. He couldn't see or experiment on individual atoms directly, so he had no insight into their internal structure. We might visualize Dalton's atom as a piece in a molecular modeling kit, where different elements are represented by spheres of different sizes and colors. While this is a handy model for some applications, we now know that atoms are far from being solid spheres. Advances in science have revealed that atoms are composed of even smaller particles, protons, neutrons, and electrons, all arranged in a complex structure. Dalton's atomic theory didn't stop at just the existence of atoms. He proposed that all atoms of a given element are identical in mass and properties. For example, every single atom of an element, such as gold, is the same as every other atom of that element. Dalton also made another crucial observation. The atoms of one element differ from the atoms of all other elements. For example, a sodium atom is different from a carbon atom. Elements may share some similar characteristics like boiling points, melting points, and electronegativities, but no two elements have the same exact set of properties. Even today, Dalton's theory holds strong. In the third part of Dalton's atomic theory, he proposed that compounds are combinations of two or more different types of atoms. An example of such a compound is table salt. Table salt is a combination of two separate elements with unique physical and chemical properties. The first, sodium, is a highly reactive metal. The second, chlorine, is a toxic gas. When they react, the atoms combine in a 1:1 ratio to form white crystals of NaCl, which we can sprinkle on our food. Since atoms are indivisible, they will always combine in simple whole number ratios. For instance, water is always H2O. In the fourth and final part of Dalton's atomic theory, he suggested that chemical reactions don't destroy or create atoms. They merely rearrange the atoms. Using our salt example again, when sodium combines with chlorine to make salt, both the sodium and chlorine atoms still exist. They simply rearrange to form a new compound. This concept was groundbreaking. It means that in a chemical reaction, the total mass of the reactants equals the total mass of the products. Imagine you have a set of building blocks. You can rearrange them to build different structures, but the number of blocks remains the same. Similarly, a chemical reaction is like rearranging these blocks to create a new structure without losing or gaining any blocks. This principle is known as the law of conservation of mass. Whether it's the rusting of iron or the combustion of gasoline, the atoms involved are simply being rearranged into new compounds. Dalton's theory provided a solid foundation for our understanding of chemical reactions. In summary, Dalton's atomic theory was the first complete attempt to describe all matter in terms of atoms and their properties. Dalton based his theory on two key principles: the law of conservation of mass and the law of constant composition. The first part of his theory states that all matter is made of atoms which are indivisible. The second part of the theory asserts that all atoms of a given element are identical in mass and properties. The third part of Dalton's theory states that compounds are combinations of two or more different types of atoms. Finally, the fourth part of the theory posits that a chemical reaction is simply a rearrangement of atoms. While parts of Dalton's theory had to be modified with the discovery of subatomic particles and isotopes, his work remains a cornerstone in the field of chemistry.